everyone, welcome to our channel Knowledge of. Friends, subscribe to our channel and click the bell icon for the latest update. आज हम कंप्यूटर ग्राफिक्स की क्लास करने वाले हैं जो कि क्लास आपका 2 है एंड दिस इज़ योर यूनिट 1 विच इज़ योर ग्राफिक्स डिवाइसेस एंड हम लोग कंप्यूटर ग्राफिक्स कर रहे हैं तो उसमें हमने जो फर्स्ट क्लास थी उसमें ऑलरेडी हमने हाफ ऑफ द थिंग्स कवर अप कर लिए हैं एंड नाउ इन दिस क्लास विल बी डूइंग योर न्यूमेरिकल पार्ट बिकॉज इसमें के क्वेश्चंस बहुत पूछे जाते हैं and that is also even though important for you. And first of all, it's a huge request from my side to all the viewers, please go through with the subscribe button and please like, share and subscribe to our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. In the terms of the questions regarding this, so we'll be starting with the first question of the session, that how much time is spent scanning across each row of pixel during a screen refresh of 1280 multiply 1024 at a refresh rate of 60 frame per second. So for that you have to find it out, and how much time is spent scanning across each row of pixel, that we have to find it out. Let's go ahead with the question. I will be writing it for you and you can just go through with that. How much time is spent scanning across each row of pixel during a screen refresh of 1280 multiply 1024 at refresh rate of 60 frame per second. So here we have to find it out. Let's go ahead with the solution here. In this solution, that resolution, we know that resolution is equals to 1280 multiply 1024, and refresh rate, as we know that refresh rate is your 60 frames per second, so that is equals to 60 frame per second, and therefore one frame of refresh every 1/60th second, we can say that. So one frame to refresh every 1/60th second, and so rows equals to, that is 1024, and therefore the time taken of the 1024 rows is equals to 1/6 as what we had mentioned here. So the time taken by each row of the pixel to refresh here, that is time taken, you have to write it on all, that is time taken by each row of the pixel to refresh is equals to 1/60th multiply 1024, that is a row, and that is equals to 0.0162 into 10 to the power minus 3 second. This will be the right answer here for this. Let's go ahead with another question, and that is also a different and important question as well. So the question is that consider the three different raster system with the resolutions of 640 multiply 480, and that is the 1024 multiply 1080, and 2560 multiply 2048. So what will be the size of the frame buffer required for each of these systems to store 12 bit per pixel, and how much storage is required for the full color, that is your 24 bit per pixel here. So here we have to find out the frame buffer sizes, and so that I will go ahead with the question. I will just write it down and you can go through with that. Another question is, consider three different raster system with resolution that is your 640 multiply 480, again is your 1024 multiply 1280, and that is another one is your 2560 multiply 2048. So what will be the size of frame buffer required for each of these systems to store 12 bits per pixel? How much storage is required for full color, that is 24 bits per pixel. So in this, the first we'll have to find out the solution here, and here that a frame buffer size, first we'll write it on. Frame buffer size equals to number of pixel or resolution multiplied by bit per pixel by 8 bytes. So here we'll make a table, and so that we'll find it out each and everything for the 12 bit per pixel and 24 bit per pixel as well. So with the same reference towards it, so as they had mentioned about it, we have to find it out for the 12 bit per pixel as well as for the 24 or per bits per pixel. So we'll make a sort of a table, so that we'll be finding out in an easy way as well. So let's go ahead here as so here we'll be making a 3 column. The first column is your resolution, the second column is for 12 bit per pixel, and the third column for 24 bit per pixel. Here for this we'll be finding out for each and everything, and that what they had mentioned about it, and even though we have to solve it out as well. So the first resolution we have is for 640 multiply 480, and the second, for that second we have your 1024 multiply 1280, and the third we have here is your, that is 2560 multiply 2048. So here for this we'll have to find it out. Let's go ahead. For the 640 multiply 480 here for the 12 bit, we'll be finding out by putting a formula here, that is your 640 into 480 into 12 and by 8. That has been written here, you can just copy it down. When we solve it out, what we'll get is your 460,800, that is your 4,60,800 bytes. Okay, for the 12 bit pixel for this was for the same as well, so we'll write it on here. The 12 लिखा था, next में हम लोग 24 लिखेंगे and we'll solve it out. 640 multiply 480 multiply 24 upon 8. So we'll just solve it out and we'll get 9,21,600 bytes. Okay, So here now we'll go ahead for the second one. That the second frame we have 1024 multiply 1280, and for this we have 1024 multiply 1280 multiply, because we're finding out for a 12 bit per pixel, so we'll multiply by this, and then we'll divide it by 8 here. So after solution we'll be finding out here is your 19,66,080 bytes. And for here that will be putting a value here, that is your 1024 multiply 1280 multiply 24 upon 8 here. So after this solution we'll get 39,32,160 here. So that's the bytes. In byte we'll represent it out. Let's go ahead with another one, and that what we have here is the another one for the 12 bit per pixel, and the frame is, the resolution is 2560 multiply 2448. So here 2560 multiply 2048 and multiply for the 12 bit per pixel, so we'll multiply by 12 and by 8. So here we'll get is 78,64,320 bytes. And for here this is for 24 bit per pixel, so we'll go ahead 2560 multiply 2048 multiply 24 divided by 8 here. So for that we will have 15,72,000, no, so 1,57,00,000, and that is your 28,640 bytes. So this is the solution for this. Let's go ahead with another one and with another question, and that what we have is the another question is that consider the two raster scan display devices with the resolutions of 640 and 480 and 1024 and 1280, and how many pixels will be accessed per second in each of these systems by the display controller, and that refreshes the screen at the rate of 60 frames per second, and also find access time per pixel here. So we'll be having to find it out for the access time per pixel as well, and so that we'll be going ahead here. So let's go ahead with the question, and the question is consider two raster scan display devices with a resolution of 640 multiply by 480 and 1024 multiply 1280. How many pixels will be accessed per second in each of these systems by the display controller that refreshes the screen at a rate of 60 frames per second, and also find access time per pixel. Okay, so we have to find it out for that, and we'll find it out for the solution as well. So in this, if I'm talking about for the solution, so here that the number of the pixel in one frame resolution, that is equals to the number of the columns, that is your width, and the number of the rows. So the number of frames in the 1 second is the 60 frame, and number of the pixels of 60 frames resolution multiplied with 60. So we'll be finding out for that, and let's go ahead with the solution here. So we'll be finding out with the solution, and that is the number of pixel in one frame or resolution is equals to number of column, that is your width, multiply number of rows, which is your height. Okay, so you have to remember this formula, because without this you are not able to find it out. It's number of the frames in the 1 second, we know very well. Number of frame in 1 second, which is equals to 60 frames. And so the number of pixels in 60 frames, and that is equals to the resolution multiply by 60. So hence for the first part, that what they had told you about it, and for the first part it is they had told you about to find the resolution. And so the resolution here, as I told you about the resolution, which is equals to 640 multiply by 4, that is 30, and the number of the pixels which is equals to 640 multiply 430, and sorry, that is a 480 multiply 60, so that is equals to 18,43,200 pixels. Okay, so we'll find it out for the access time per pixel, and that is equals to 1 upon total time. So 1 upon total time is 640 multiply 480 multiply 60, that we had represented here, and in this we'll be finding out 54.25 into 10 to the power minus 9 seconds. This will be your access time per pixel. Let's go ahead for the second one here only, that is your for the resolution we have here is your 1024 multiply 1280, and number of pixel equals to 1024 multiply 1280 multiply 60, so it will count as 70, that's 7 crores 86 lakh and 43,200 pixels here. So 786,432,100 pixels. So for that, the access time per pixel equals to 1 upon total time, which is equals to 1 upon 1024 multiply 1280 multiply 60, and that is equals to 12.71 into 10 to the power minus 9 second. Okay, so now we'll go ahead with another question, another different question, that is also an important one, and that has been also asked here as well. So in the same while we'll go ahead here, and that is another question. The question is, a raster scan display supports the resolutions of 1024 into 800 or with up to 18 with up to 16 million colors. What will be the size in the bytes of the frame buffer that is used in the system? So that what we have to go on through with it. So let's go ahead. The equation is, a raster scan display supports a resolution of 1024 into 800 with up to 16 million colors what will be the size in bytes of the frames buffer used in the system. So here for the solution, the 16 million colors, so here that 16 million colors is represented by 2 to the power, that is your 24 colors, and it means we need 24 bit per pixel to store the color value. And since the resolutions we know that 1024 into 10 to the 800, and for hence the bytes required in one frame is equals to resolution multiply 24 by 8 bytes. So let's go ahead with the formula here. Bytes, so here that is your bytes, that is the bytes required in a one bytes required in one frame buffer equals to resolution multiply 24 by 8, and for that we have 1024 multiply 800 multiply 24 upon 8, and we'll solve it out. We'll find it out. 2 into 2.4 into 10 to the power 6 bytes. Let's go ahead with another question, and that is also an important one, and with the reference towards the question here, that the question is, if you want to resize a 640 into 480 image to one that is of 1024 pixel wide with the same aspect ratio, what would be the height of the resized image? So that what we have to do it. Let's go ahead with the question here. So the question is, if we want to resize a 640 into 480 image to one that is 1024 pixel wide with same aspect ratio, what would be the height of the resized image? So here in this we know that 640 by 480 is equals to, of course, that is 640 by 480, which is equals to 1024 by rho, and that is your we can say that rho equals to 1024 multiply 480, and that is by 640, and when we solve that out, we'll find it out 768 pixel. So here now we'll go ahead with another question, and that is, the another question is that what will be the size of 1024 multiply 1280 image at 300 pixel per inch. So for that we'll have to find it out, that is what will be the size of a 1024 multiply 1280 pixel image at 300 pixels per inch. So here in this, that the size is equals to that the resolution, that is your number of rows or a column, and the number of the pixels per inch. For that we'll find it out for the rows size as well. So here the solution will be size equals to resolution, that is row or column, by number of pixel per inch. For that width, then width equals to 1024 by 300, which is equals to 3.41 inches, and per height, which is equals to 1280 multiplied that is by 300, so that will be 4.26 inches. So now we'll go ahead with another question, another different question, and even though that is also an important one, and that has been asked in many times in the examination paper as well. So the question is that suppose we have a computer with a 32 bits word and transfer rate of 1 that is MPS, that million instructions per second. How long would it take to fill the frame buffer of 300 dpi, that is dot per inch, laser printer with a page size of 8.5 inches and 11 inches? So that has been asked, as I told you, that has been asked many times in the examination paper. So we'll go ahead with this as well. So let's go ahead, and hopefully this will be the last questions of the numerical part, that what we'll deal with, and then we'll discuss some of the things related to the theory as well. So in that same aspects, first we will be going ahead with the question. So here we have a question, and that is the question is, suppose we have a computer with 32 bits per word and a transfer rate of 1 MIPS, that is your million instruction per second. How long would it take to fill the frame buffer of a 300 dpi, which is your dot per inch laser and laser printer with page size of 8.5 inches by 11 inches. So let's go ahead with solution, and that the solution we have here is to be as follows. That is the frame buffer size, if I'm talking about frame buffer size equals to 8.5 into 11 inches. So 8.5, 11 into inches, so the inches is we have a square as well. So here we have 8.5 into 11, the inches is 300 square, and where we'll get it out, and that is your 1 inch equals to 300 dpi, and for that is 841500 dots, which is equals to 841500 0, that is your n bits. That is the simple conversion here. Let's go ahead in a detail here as well. After this we'll be verifying, say 1 dot is equals to, like we are going to say is your 1 dot equals to n bits, and this the transfer rate equals to 1 MIPS in the same case. And then we will be having 1 into 10 to the power 6 word per second, and that is your 1 instruction is 10 to the power 6 word. You can just write it down. So for that, 32 into 10 to the power 6 bits per second, and your 1 word equals to 32 bits. For the time required to fill the frame buffer, that is equals to 8415000 n upon 32 into 10 to the power 6, and which is equals to 0.263 n seconds. And if n equals to 4, then time taken is equals to 0.263 into 4, which is equals to 1.052 second. So that is the time taken. We'll have find out. Let's go ahead with the theory portion as well. Now that is the line generations we are talking about, and in this the line generations will go ahead with the deep knowledge of line generations as well. In that the line generations, that the points and the line, the combinations of the point like polygons, that the combinations of line, and a basic building block for the output of that is your computer graphics, that's why it is called primitives, and that the points in the straight lines are the simplest components of any picture, and other complex output primitive which can be used to construct a picture are that circles, conic sections, quadratic circles, surfaces, splines, curves and surfaces, polygon, color, area, and character strings as well. Talking about the scan conversion, that is the process of line and circle drawing algorithm and of the converting basis. So low level objects into the corresponding pixels map that represent it, and this is often an approximation to an object since the frame buffer is a discrete grid as well. In the approximation algorithm and its criteria, if I'm talking about, there are the algorithm, that is your DDA, that is your digital differential analyzers line drawing algorithm, or we can say that the symmetric DDA algorithm as well. The second algorithm is that we'll discuss about it, and that is a Bresson-Sum line drawing algorithm. The third algorithm we'll discuss about it, that is your midpoint circle drawing algorithm, and the fourth is your Bresson-Sum circles drawing algorithm. About the criteria, if I'm talking about, so the first criteria is the line curve should appear straight in shape, and line and curve that should be terminate accurately, line and curve that should be constant density, line and curve that brightness independent of the slope and the line length, and line and curve that should be drawn efficiently as well. Let's go ahead with the detail. What do you understand by point? So what do you understand by the point here? With this reference towards a point, that position in a plane that is known as point, and a point that can be represented by any order of pair of number, like in the form of x comma y, and that where x is the horizontal distance and the origin from the origin, and the y is the vertical distance of the origin. So that has been represented by the origin. I will be representing in the axis here. This is an x-axis, this is an y-axis, this is your origin that is at 0, 0, and here is a point P, so that is x comma y as I told you. So from this is your y distant and this is your x distant. Okay, so from the origin here. So now we'll go ahead with the detail about it, and that the another question what they can ask you about, that derive the equation from the intercepts from the line and find out the conditions for which the two lines are perpendicular or are parallel. So for that we will be having the solution with reference towards it, a line that is parallel and not. So there is a very deep discussion about it with the tan theta, that the case will discuss about it, and there is a derivation that has to be implemented here, and where m1 m2 and 1 plus m1 m2, that will find it out for the equation. So if both the line are parallel, then the angles that should be 0, and for that the equation will be find it out like a1 b2 equals to b1 a2, and of course for if the both are perpendicular, then the angle should be 90 degree, and that is your a1 a2 plus b1 b2 is equals to 0 here. So then that will be the finding out here. And they are the two possible cases for the both line are parallel, and of course the both are perpendicular, and then the angle should be your 90 degree here. And if they are parallel, so the angle between them is of course your 0 here. So with the same case, we have a two cases as I told you about it, and that is the case one we have, and that is if both line are parallel, then angle should be 0, and for that tan inverse m1 minus m2 upon 1 plus m1 m2, that is equals to 0. And for that if we will be changing it out, and with closing the tan here, so we will be finding out m1 minus m2 upon 1 plus m1 and m2, which is equals to 0. And that is similarly m1 minus m2, because this will goes to the 0, so that multiply with 0 and will be ended. So m1 minus m2 equals to 0, and we can this minus sign comes towards the right side, so we'll change the sign, and that is m1 equals to m2. So that is the slopes are equal, and if the slopes are equal, so it's that a1 b2 is equals to b1 and a2 here. So for that, the another case, the different case, the case 2 we have, and which is your if both are perpendicular, then angle should be 90 degree. So in that same case, if I'm talking about, so here we'll be finding out for that 90 degree which is perpendicular, and in that same case we'll be finding out tan inverse, that is m1 minus m2 1 plus m1 m2, which is equals to pi by 2, and tan 90 has been represented by pi by 2, and here in the same case m1 minus m2 upon 1 plus m1 m2, which is equals to tan pi by 2, and tan pi by 2, that tan 90 is equals to infinite, as if you had learned trigonometry and if you had gone through with the 10th class till math, you will finding out the value and you had learned that. m1 m2 equals to 90 degree, and which tends to m1 m2, that is equals to minus 1, or we can say that tan inverse a2 b1 minus a1 b2 upon a1 a2 plus b1 b2, which is equals to pi by 2, and same for that, we will be having a1 a2 plus b1 b2, which is equals to 0 here. So this is the solution. Now let's we'll end up with here, and first of all, it's a huge request from my side to all the viewers, please go through with the subscribe button and please like, share and subscribe to our channel, so that many and maximum people can get the information at once. And even though you can also enjoy the video as well, and we'll be continuing with the next class. We'll discuss about the line segment and many more things in terms of it, and related to that as well. So here in the computer graphics, what we have to cover up, and here the first unit is your graphics devices in computer graphics, that is we have to cover up the introduction to and line generations, the types of the computer graphics displays, random scan displays, raster scan display, frame buffer and a video controller, points and line drawing algorithm, circle generating algorithm, mid part point circle generating algorithm, and a parallel version of these algorithm, that what we have to discuss here. In the same case, in the unit 2, we have to discuss about the transformation, where the unit name is, and the transformation, that is the basic transformation, matrix representation and homogeneous coordinates, composite transformation, reflections and shearing, and windowing and clipping. In this, that we have to discuss about the viewing pipeline, viewing transformations, 2D clipping algorithm, line clipping algorithm such as your Cohen-Sutherland line clipping algorithm, Liang-Barsky algorithm, line clipping against non-rectangular clip window, and polygon clipping, Sutherland that is your Hodgman polygon clipping, and of course the Wheeler and the Atherton polygon clipping, and the curve clipping, text clipping as well. In the same case, we have to discuss about the unit 3rd, that is your 3-dimensional, and in this, that the 3-dimensional 3D geometric primitives, 3D object representation, 3D transformation, 3D viewing, projection and 3D clipping as well. In the unit 4, what we have to cover up the curves and surfaces, the quadratic surfaces, the spheres, ellipsoid, blobby objects, introductory concepts of spline, and of course the B-spline and bisers, curves and surfaces, and the hidden line surfaces. We have to cover up the back face detection algorithm, and in the same case, in the back spheres, the detection algorithm, the depth buffer method and A buffer method, scan line method, basic elimination method, and models, and that the ambient line, diffuse reflections, the spectacular reflections, and the Phong model, combined approach, that bond model, intensity, attenuations, color considerations, transparency and shadows as well. So first of all, it's a huge request from my side to all the viewers, please go through with the subscribe button and please like, share and subscribe our channel, so that many and maximum people can get the information at once. And even though you can also enjoy the video as well, and you will be finding out each and every video here outside. And as of now, we are dealing with artificial intelligence, as well as we are doing the data warehouse and data mining, and as well as the database management system with reference towards it. Even the reasoning we are doing here at a time, and now we're doing computer graphics as well, that is the second classes of it. And after that, we'll be discussing many more subjects in terms of it, so you can go through with that. And please like, share and subscribe to our channel, so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. Thank you, thanks for subscribing us. Thank you, hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion in the comment box. Thank you.